It's a pleasure to have Lavinia Picollo with us. Lavinia with her PhD in Buenos Aires, and then she was assistant professor in Munich and a lecturer in London, and now she's an assistant professor in Singapore, and she's known for her work on truth, reference, deflationism, and related areas. And today she's going to talk about arithmetical pluralism. The virtual floor is yours, Lavinia.
Thank you very much, Luca, Francesca, and Fabrice. It's nice to give a talk in Europe, so people don't forget about me. This work is on something else. Yeah, I haven't worked on this much so far, only for a year or two. This one is on arithmetical pluralism, and it's joint work with Dan Waxman, as you can see there. So let me just start. You have the abstract. I changed it a bit because I finessed some things. I hope it's that and not the opposite. So I'm just going to start telling you about arithmetical pluralism and actually mathematical pluralism, which is a more general view. I take it that mathematical pluralism is the view that every consistent mathematical theory is true in its own language, of course, and therefore as legitimate as any other. Of course, some theories might be better than others for a particular purpose, and of course that means that we'll choose one over the other. But from a theoretical standpoint, I suppose we can say that a pluralist would say, no, they're all equally good. If you know about logical pluralism, it's a similar view, right? And arithmetical pluralism is similar, except that it focuses on arithmetical theories, right? So every consistent arithmetical theory is true in its own language and therefore equally legitimate as any other, at least from a theoretical standpoint. And these views of pluralism is quite popular. I mean, I think Carnap was perhaps the first one to propose something like this, and recently they became more popular because they seem to be in good standing to solve the question that Ben-Asaraf poses for the Platonist, for instance, the epistemic challenge. So this is the question, how you get to know about these mathematical entities you have no contact with, you cannot see, you cannot touch, you cannot perceive, you don't have any causal relations with, right? So it's very easy how I get to know this glass, I can see it, I can touch it. How do you get to know about the natural numbers, for instance? And so, for instance, Balaguer famously responds to this challenge with his plenitudinous Platonism, which is a view that says that all mathematical objects that could exist, that logically possibly exist, actually do exist. And therefore, every theory that is consistent is talking about some bit of the mathematical realm. And this is how we get to know things about these things and these natural numbers just by adopting any consistent theory. Well, maybe not the natural numbers, but at least some abstract objects, right? But this is not the only view that arrived at a form of pluralism with coming from similar motivations, that is to solve the puzzle of our mathematical knowledge. The other one is mathematical conventionalism, which is what we got here, which is a view that basically our mathematical theories, mathematical truths are true by linguistic convention. So they're a product of our decisions to use terms in a certain way or other. And this way, if you ask me, how do I know that the axioms of my theory are true, I'll say, well, I mean, these are actually linguistic conventions, right? They're true by linguistic convention, and therefore I don't have to do any more explaining besides that. And so I get mathematical knowledge for free. So these views are, Platonism and mathematical conventionalism seem to motivate mathematical pluralism and arithmetical pluralism, but one can come from different angles to the mathematical pluralism view. However, this is why they're quite attractive, these views. Now, there's been a challenge for these views kind of recently. The first bit was by Putnam, and the second by Kulna. So I have two quotes here. This is what, for instance, so Jared Warren is one of the main proponents of conventionalism, of mathematical and arithmetical conventionalism. And in this paper in 2015 that I'm going to quote a couple of times, as you'll see, he defends, he suggests that mathematical conventionalism actually entails arithmetical pluralism. And so he takes this challenge, what he calls the puzzle of arithmetization, which is a challenge for arithmetical pluralism, to be a challenge in turn for conventionalism. And it kind of reads that way. So let me read for you these quotes. So this is by Putnam. Once we grant that there is at least one mathematical fact, which is not simply our stipulation, that, for example, the consistency of our stipulations practices is not itself another stipulation or practice, then logical positivists or Wittgensteinian accounts of logical and mathematical truth are seen to be bankrupt. So basically the idea is, if every consistent theory, for instance, arithmetical theory is equally legitimate, and therefore which one we work with is a matter of choice, then how is it possible that consistency is not itself varying along with our choices? And why would he think that? The idea is, why would he think that consistent facts about consistency vary along with facts about numbers, about arithmetic? Because of what Kulna tells us here. This radical form of pluralism, he's talking about Carnap and then Reichenbach, came to be challenged by Gould's discovery of the incompleteness theorems. To begin with, through the arithmetization of syntax, the metamathematical notions that Reichenbach takes to fall within the prominence of critical investigation, that is, probability and consistency, were themselves seen to be part of arithmetic. Thus, one cannot, on pain of inconsistency, say that there's a question of truth and falsehood with regards to the former, but not to the latter. So the idea is, look, to formulate your view, you need to formulate the view, for instance, arithmetical pluralism, you need a notion of consistency, right? Because you're saying all consistent theories are true in their own language and therefore equally legitimate. So you need a notion of consistency. And that notion of consistency has to be common to all the arithmetical theories it's supposed to apply to, right? However, those arithmetical theories can themselves express a notion of consistency and facts about the consistency of theories. So if those are a matter of choice, that turns just by arithmetization, right? So if those are a matter of choice, that turns consistency issues a matter of choice as well. But you needed that to be independent of the choices. You needed that to be a fact. So here's another way to put it, the way I put it here in the puzzle of arithmetization. On the one hand, arithmetical pluralists are appealing to syntactic facts, right? Regarding which theories are consistent and which aren't. But on the other hand, they're saying we can choose our arithmetical principles as we please, as long as the choice is consistent. But by Gould's arithmetization technique, we know that syntactic facts are linked to our arithmetical theories because our arithmetical theories are able to express those syntactic facts and prove some of those. So how is it possible that syntax is a matter of fact and arithmetic is a matter of choice or convention, right? This is the puzzle. It might be a bit unclear, so I thought let's formalize it, because anyway, we're going to see that there's a response to this puzzle by Warren himself. He's trying to defend his version of arithmetical pluralism coming from conventionalism, and this requires us to get into the details of the problem. And what we're going to do, what we are going to do in this paper is we're going to say that, so we accept that Warren's response is correct. We agree with it, but there is another there's a variation of Kellner's and Putnam's argument that is immune to Warren's response and actually does go through. So we are going to suggest that arithmetical pluralism is in trouble for precisely the reason that Putnam and Kellner are pointing at, which is syntax and arithmetic vary along together, and so you cannot have syntax being a matter of fact and arithmetic a matter of choice. But the argument that Kellner makes explicitly here and that Warren responds to is a bad argument for that thesis. So we're gonna first revise this argument, see why it's bad following Warren, and then give our own argument and see why that one is immune to the criticism. So here's a formal setup. So we say LPA here is the language of first order arithmetic. So it has a signature. Nat is a predicate for natural numbers. And we have 0, successor, plus, and times. Actually, I made a mistake. Those n's shouldn't be there. Please ignore them. That's a typo. We just have the typical symbols of the language of arithmetic here. And PA is the theory we all know about. It consists of these axioms. Note that the quantified axioms are all relativized to this predicate being a natural number. This doesn't really affect the theory because we are saying that we have this extra axiom here saying that 0 is a natural number. So this formulation of PA is equivalent to the ones we're more used to. And we have induction, right, for all phis in the language. Now, as you know, Go's arithmetization technique consists in assigning an expression to each natural number, right? And that expression is the expression that the natural number codes, right? And then also every sequence of expressions gets a natural number, right? So we can regard the language of arithmetic as talking about the expressions or sequences of expressions that the numbers code instead of the numbers themselves, right? Via the coding, we can think of the language of arithmetic as talking about expressions of any language, and in particular, expressions of the very same language, LPA. So this is standard. If n is the code of a sentence phi, this, which was the name for number n, is now taken to be a name for phi. So this is n many successor function symbols followed by 0. So it's what we would have called the numeral of n is now taken to denote the sentence phi directly via its code. And so we write it like this instead. So the numerical name for phi. And we also know that the language then using the coding, the language LBA using coding contains a formula, which I write here, prov n, that defines the property of being a code of a theorem of PA. So that defines the notion of provability in PA. And I'm assuming that this is done in a natural way, meaning that it kind of follows the standard definition of provability that we have in mind. Basically, provable is something that is either an axiom or follows from the axioms using some of the rules that are admissible in the calculus. So we're assuming a background calculus here, and all the theories we're going to talk about are formulated in this calculus, which is a classical calculus, and so on. And so note that if this is the case, then this bit here, this formula there says is not provable this sentence. So this sentence, the sentence 0 different from 0, is not provable in PA, right? And this sentence, because it's saying that there's a sentence that is not provable in PA, in particular 0 different from 0, can be taken to express the consistency of PA in the language of PA, right? So this is standard. Now, we also know by Go that if PA is consistent, then adding this sentence to PA or its negation results in a consistent theory, right? Because what Gödel proves is that this sentence is independent of PA, so it's neither provable nor refutable. So here's the argument that Gödel gives in more formal terms. Look, both PA and PA plus not con PA, so both PA plus PA saying, plus a sentence saying I'm inconsistent, are presumably consistent arithmetical theories. Why? Because we believe kind of that PA is consistent, right? And we have this theorem by Gödel saying if PA is consistent, then this one is consistent as well. So we kind of believe these two theories are consistent. This means that the pluralist, the arithmetical pluralist, is committed to saying that they're both true in their own language, right? And thus equally legitimate. This is what arithmetical pluralism says. If it's consistent, then it's true in its own language, and therefore it's legitimate. But note the following. This theory, it seems to be proving a false arithmetical statement, right? Namely, that this bit is, namely that bit which says PA is inconsistent. And not only that, it's only proving its own inconsistency. Because if it's saying that PA is inconsistent, since the theory is an extension of PA, then it's also saying that the theory itself is inconsistent. But we were assuming they were consistent, right? So this contradicts the first premise, or if you wish, the second one. So either PA is inconsistent, or this theory is not true in its own language, right? So either PA is inconsistent or arithmetical pluralism is wrong. Since we believe that PA is not inconsistent, Kellner concludes arithmetical pluralism is wrong. And Putnam had something similar in mind, except that he's Putnam and he had to write it in a very cryptic way. But I think it's clear that he had something similar in mind. Should I clarify anything here? I could stop and go back if necessary.
I have a small clarification question.
Mm-hmm.
So the first premise is just because you never said, and I wanted to know whether they say it or not. It presupposes finitist method, right? Because you cannot prove that PA plus not con PA is consistent if you work with finitistic method. But if you go with infinite rules, then you can prove it. You can prove that it's not consistent. So all this argument goes under the assumption that you only work with finitistic method. Is that?
Yeah, so I'm assuming basically that, so basically when I say theory, for now at least in this argument, what is meant is a first order theory. So a theory formulated in a first order calculus for classical logic, meaning only finitary proofs and
Okay.
finitistic methods.
Okay.
Yes, perfect. So we need Gödel incompleteness around. This is key. Note that if we had infinitary methods, so for instance, if we had the omega rule around, then the pluralist would be saying something trivial, because the pluralist wouldn't. The point, I guess the motivation for the pluralist, what motivates as well a bit of Benasar's epistemological challenge, and what motivates Balaguer's Platonism and conventionalism itself, in part, is the fact that our arithmetical practice doesn't really pin down a complete theory, right? They're undecidable expressions. And so for instance, what the conventionalist and the pluralist wants to say, look, it doesn't matter how you you could make choices that don't affect the truth of your theory. This would be the point, because if you think about it, we have PA, right? And I could ask you, and I realize that I cannot prove or disprove con-PA using the axioms of PA alone, right? And then I ask you, okay, but which one is the correct theory? They cannot be both correct at the same time, right? PA plus con-PA and PA plus not con-PA. So which one is the correct one? I could ask you that. And in a way, there is no answer. I mean, you could say, no, obviously PA plus con-PA, because you could say that, but there are other independent sentences around. And the same question would arise there. And given that those sentences are completely independent from PA, or from whatever theory we choose to start with, there will always be some independent ones as long as we use finitary methods, then I wouldn't be able to answer that. So then you could ask me, oh yeah, so you don't know. So how do you know that the theory we have now is the true one, the one that talks about the real natural numbers, right? So I could put you in an epistemological conundrum, basically. And the way that these people have to answer the challenge is to say, all of them are correct. You cannot go wrong here. And so if we were using infinitary methods, none of this would be necessary, because there would only be one theory. PA plus the omega rule is a complete theory, and there wouldn't be any room for choosing anything. So the whole problem would be solved. This is their theory, all others would be inconsistent. So that's our answer, right? So this all the discussion presupposes that we only use
that's exactly
yes.
what the whole discussion presupposes, which I'm fine with. I'm really very fine with. I'm just, since I never saw it in your slides, I was wondering why maybe it's so evident that they don't need to claim it, but to me it's a big premise, which I'm fine with.
Right.
But,
Fair. Yes, that's definitely a premise.
Okay.
Great. So the argument seems quite solid, but if we look at it, if we give it a second glance, then we'll realize that actually it's quite bad. Because, and I'm totally, we're totally with Warren here. Note that what the arithmetical pluralist is saying is that every arithmetical theory is true in its own language, right? Obviously, if I have PA plus con-PA on the one hand and PA plus not con-PA on the other, then they cannot be both true, period, because they contradict each other, right? So what do they mean when they say they're both true? They're true in their own language, which means that the expressions that occur in the sentences, in the theorems of the theory, in the expressions of the theory, have different meanings. The meaning, for instance, according to a conventionalist, is given by the axioms, and those axioms are stipulations that we make, right? We decide to use a theory in the symbols of the theory in a certain way by stipulating certain axioms. If we stipulate different axioms, then the meaning is different, right? So Warren says con-PA doesn't mean the same here as it does here, right? They're different axioms. And only here is that we take this sentence to mean PA is consistent. Because only when our theory is interpreted as talking about the standard natural numbers is that we take its expressions to talk about the syntactic expressions. Only the standard natural numbers were being used to code up the expressions of the language. And therefore, only under this interpretation is that we take expressions of PA to mean syntactic things. Now, this theory doesn't have that interpretation around, because this theory is omega inconsistent. And so in this theory, you cannot read the expressions as talking about syntax because the coding is gone, because the objects are not the same. The objects the theory is talking about cannot be the same. So Warren concludes, look, the mathematical pluralist can perfectly coherently hold that PA plus not comp PA is true in its own language, and that PA is consistent at the same time, period. He has this citation here that I think is quite interesting to read, but I'm only going to read the last sentence, in which he says, look, it's completely coherent to suppose that consistency is a matter of fact, while arithmetical truth, even for consistency centers, is a matter of convention. So the answer that Warren's given here to this argument is like, this premise is wrong. This theory is not proving a false arithmetical statement, because this, in that theory, doesn't mean PA is inconsistent. It means something else. So that's the answer. And we think that this works very well. I totally believe this. I think if we, the situation is similar as what we learn from Carnot's frameworks. The meaning of the expressions in each framework is different from the meaning of those expressions in another framework, and we cannot read them, take them as face value if we are not in that framework. So here it's something similar. However, we believe there's still a big challenge for the arithmetical pluralist. We're calling it the puzzle of applicability instead of the puzzle of arithmetization, because it has to do with the fact that arithmetical theories are theories that have to work for us as arithmetic does, in the sense that they have to help us count things. They have to be applicable in the same way that we apply arithmetic in our language. So I'm going to show you these two things, and I think together they are enough to allow us to conclude that arithmetical and syntactic facts are entangled in such a way that is not coherent to say that arithmetical facts are a matter of choice and syntactic facts are a matter of fact. Thesis 1 says that the arithmetical pluralist cannot regard PA plus not comp PA as a consistent arithmetical theory. I'm going to show you that. And so this means that Warren was wrong when he says that the mathematical pluralist can perfectly coherently hold that this is true and PA is consistent, that theory is true in its own language and PA is consistent. We actually show that's not the case, but we don't do it using Putnam's Kellner's line. And the second thesis is that arithmetical pluralism is incompatible with there being two arithmetical theories, T1 and T2, that extend PA and that prove incompatible claims, or at least syntactically incompatible claims, in the sense that one proves phi and the other one proves not phi, even though the meanings of these sentences will be different in each theory. So note that I've been talking about arithmetical theories, and I've been talking about, I just said that the pluralist cannot regard this theory or T1 and T2 as consistent arithmetical theories. And this word arithmetical there is very important for the following reason. So what counts as an arithmetical theory? It's important to note that it's not about syntax exclusively. It's neither necessary nor sufficient that the theory is expressed in the language of PA or an extension of that language. Why so? So think about the following. Think about, for instance, a theory formulated in this language that consists only of one axiom. For instance, this one. It could also be 0 equals 0. It could also, well, maybe not that one, but it could also be 0 is not the successor of any number, or any other axiom, any phi that you want from the language. Now, we could reinterpret this.
Lavinia, can I just interrupt you 1 second? There's a clarification question which I had missed just a couple of minutes ago.
Yes.
Ricardo Aguilera. So he's asking, so is Warren saying that PA plus the negation of comp PA is actually T equal PA plus the negation of the consistency of T? You can see it in the chart
I'm gonna look at it in the chat.
I can try to clarify, but I realized after typing it and you scrolling down a little bit more that it's not what I said. So I think I can like re-ask the question at the end, because I think
I think I understand your question. The answer is no.
Okay.
PA plus not con PA is not a theory that says I am inconsistent.
Okay.
It's a theory that says PA and PA is inconsistent.
Okay.
So a fragment of me, of myself, is inconsistent, not just
That
the whole
helps.
theory. But of course, if a fragment is inconsistent, then the theory is inconsistent. So yeah.
Okay, thank you.
No problem. Okay, so the point is, like, I could take any theory that I want formulated in the language of LPA. For instance, I could take any sentence phi here. I chose not con PA because I thought it was suggestive, but a theory could be any set of sentences, right? And I could assign the meaning to that sentence, for instance, that snow is white. So I could take that sentence to mean snow is white. Because I can interpret theories the way I want, right? So I guess the idea would be, imagine I introduce this sentence not con PA to English, and every time I use it, I'm pointing at snow and saying, no, so it's not black, not con PA. So it turns out that you realize that not con PA in my language, I just added this string of symbols, and I decided by stipulation, because I can, right? Because the symbol is arbitrary, that the sentence means snow is white. Would that mean that I have a true arithmetical theory in my hands? Obviously not. The theory is no longer arithmetical, right? In a way. Moreover, imagine that the sentence I chose, instead of being not con PA, is 0 is the successor of 3 numbers, right? Like the string of symbols that we would take now to express 0 is the successor of 3 numbers. But I take it to mean in my language, snow is white. That would mean that in PA, the sentence is false, but in my theory, the sentence is true. So arithmetical pluralism is valid, is true. Because I just showed you 2 theories that are arithmetical, both of which are true. You would be like, I don't think so. That's not an arithmetical theory, right? The theory that just has this sentence and you're interpreting it in a very weird way is not an arithmetical theory. So just the fact that it's expressed in the language of LPA is not enough. And also it's not necessary. First of all, because we could have chosen a different language, right? We could have chosen a language that contains other logical symbols that are interdefinable with ours, or I could have chosen to do arithmetic in English or in Italian or Spanish or any other language. So it's not about the language, it's not about syntax, right? What is it about? So Warren has this, he tries to answer the same question. He calls it the puzzle of pluralism, because he thinks this puzzle affects every version of pluralism. Basically, you need to say, if you're going to be a pluralist about something, you need to identify that something somehow. So if you're going to be a pluralist about logic, you need to tell me what counts as a logic first. And here you need to tell me what counts as an arithmetical theory first. And he tries to pin down this notion in terms of similarity of inferential structure of English to the inferential structure of English arithmetic. So the idea would be a theory is an arithmetical theory if it contains symbols that had the same inferential behavior or similar inferential behavior to the inferential behavior of the symbols that we use in arithmetical English. This is basically what he's saying here. The important bit of the citation that I have here is this bit. I've been assuming that a formal system of rules functionally identical to first-order Peano arithmetic captures the inferential structure of arithmetical expressions in our language. So he's been assuming that PA behave like, if the axioms of PA hold, then we have an arithmetical theory. But the actual inferential uses of arithmetic in natural languages like English go beyond this. to include rules for applied arithmetic as well, right? So what he's saying is an arithmetical theory would have to kind of include the axioms of PA, or maybe the axioms of Robinson arithmetic or something like that. But it would also be expected to satisfy certain applicability axioms. And I am pretty sure that this includes instances of induction that go beyond formally of the language of arithmetic. So for instance, we use arithmetic to prove things about sentences formally by thinking about the logical complexity of a formally, or to prove things about proofs, thinking about the length of the proofs, right? Induction of the length, and we do these things, and these are part of our applied arithmetic practice, right? So to make it a bit more rigorous, we came up with this sufficient condition for arithmetical theory, which is any recursively axiomatizable extension of PA with axioms of the language, in the language of PA, or a translation in a suitable language, in a kind of isomorphic language, is an arithmetical theory, just in case it coheres with our arithmetical practice, right? And this means, this includes treating induction as open-ended. And by this, I don't mean adopt induction for whatever predicate you want, because we know that, for instance, vague predicates could get us in trouble, and other predicates like truth could also get us in trouble. But in general, if everything is all right, just like we do in English, we should be willing to extend our induction principles to new vocabulary. So having this in mind, I'm going to give you arguments for thesis 1 and thesis 2. And this is going to allow me to conclude that there is an interdependence between syntax and arithmetic, and therefore kind of Putnam and Kohlmeier seem to be right about this. Remember that the arithmetical pluralist and also the mathematical pluralist need to talk about a syntax theory. They need to have a notion of consistency, and therefore they need to have a notion of proof and provability in a theory, and this means they need to have some kind of syntax theory. I'm going to say they should accept this one, but the arguments we're going to give also apply if you accept similar theories, equivalent theories that are expressed in very different languages. So this is a toy example. This syntax theory is formulated in a language that contains a predicate for is a syntactic object, and then all the arithmetical symbols, but instead of having no index, no subindex, they have an S as subindex to differentiate them from the others. As you know, this is not standard for a syntax theory, but it's equivalent to the standard ways of defining a theory of syntax in a formal language. So for instance, there is a work by Halbach and Lee that is not published yet, but proves this very easily, but also some papers by Corcoran and so on. So our syntax theory is basically PA, except that we replace every symbol in the signature of LPA with the corresponding symbol here in the signature. And also induction is treated as open-ended because our syntax theory also applies to things, to different domains. So in the intended interpretation, this predicate will be true of all the finite strings of symbols of the language of arithmetic. If we wish, we could extend this to talk about other languages as well. And also it will be true of all finite sequences of strings of symbols. So this language will be able to talk about expressions of the language of PA and also proofs in a theory formulated in that language. Now note that this is, if epsilon is a finite string of symbols, we write Quinian codes to denote a name, to talk about a name for that expression in the language, which we will have. And now we don't have the index n there, because this is the real name in the syntax theory. That is the theory that's supposed to talk directly about syntactic objects and not via coding anymore. And again, this theory contains provability predicates for any recursively axiomatizable theory formulated in the language of PA. So we can talk about theories formulated in the language, and also it can define the notion of is a proof of, and therefore it's provable in. And I'm assuming that this is done in a natural way as well, meaning in an unusual way, in the same way as we see in textbooks and stuff, how you define what a derivation is and what's provable in a theory. And therefore, using this formula, it can express the consistency of each of these theories, but now not via coding directly, right? So note that here there is no index, there is no subscript or anything with an N. Okay. There's an obvious translation from the language of arithmetic to the language of syntax. That one, which basically replaces every symbol with its counterparts, every symbol in the signature of the arithmetical language with its counterpart in the syntactic language. Why is this important? You'll see in a minute. We have an inverse function that does the opposite, right? So that is that one. If I take a syntactic expression and I apply this function to it, I get the corresponding arithmetical expression, and vice versa. Okay. Now I'm going to build this big language, which consists of the arithmetical language plus the syntax language. And I call it NS. Actually, NS also contains a one-place function symbol, numeral. And this is the important bit. If T is a recursively axiomatizable theory formulated in language of arithmetic extending PA, then NST consists of T plus the syntax theory on top of T. So that our theory extending PA, to that we add the syntax theory, and on top of that we're going to add these two clauses, which are intended as a recursive, primitive recursive definition of this function symbol that I told you we just added to the language. This function defined by this symbol maps the numerical 0 to the syntactic 0, and each syntax, and then you can see that the successor of a numerical of a number is mapped to the syntactic successor to the image of that number. So basically what this function is doing, note that is appropriately defined because it follows the primitive recursion schema. It maps the numerical 0 to a syntactic object and the numerical 1 to another syntactic object, and so on, right? And we can prove that this function is bijective in this big theory.
Sorry,
Yes,
why
sorry.
do you need this function? Do you need it, or you just add it?
Yes. No, I'm gonna need it.
And why do you need it?
You'll see in a minute.
Ah, okay.
It will be very clear in a minute.
Okay.
But if I put, the idea is if I put those theories together, I will be able to define a function that maps 1-to-1 every number that I've got to every syntactic object that I have. That's the idea. And this is what this proves. But I do it in the big theory that I told you about, right? The one that contains the syntax theory, my theory T, which is an extension of PA, and these two clauses. Another thing that this theory contains, and it's very important, is that when I add my arithmetical theory, my extension of PA, I extend the induction schema of that theory to every symbol of the new language. So formally containing this symbol and formally containing the symbols of the signature of the syntactic language will be giving me instances of induction, of numerical induction, and vice versa. I'll get instances of syntactic induction for every formula of the language. If I have that, but this I'm assuming, because I'm assuming the syntax theory has open-end induction. If you have that, then you'll be able to prove that this function is bijective, which is exactly what this says. And because of that, you're going to be able to prove observation 2, which says the theory is proving uniformly a biconditional between each formula and its translation, which means that if my theory formulated in the language of PA, extending PA, proves something, then the bigger theory with the syntax on top proves the translation of that, the syntactic version of it, and vice versa. If my syntax theory was proving something, then the bigger theory will prove its numerical version. Something the syntax theory can allow me to do is to show that if T is consistent, then PA is consistent. And this is because T is an extension of PA. So if my syntax theory can do that, then of course the bigger theory can do it as well. Knowing this is the main argument, and I should be done soon. The argument from which the two theses follow, which says the following. So assume the arithmetical pluralist regards T as a consistent arithmetical theory. That means that they must be willing to extend the induction schema that T has to new symbols, right? Okay, knowing that, we also know, so we literally know that they are committed to the truth of T in its own language with induction extended to formally of the extended language. Why are they committed to the truth of T in its own language? Well, that's what arithmetical pluralism is about. Give me a consistent theory, I'm committed to its truth in its own language. Give me a consistent arithmetical theory, then I'm also committed to extended induction to new symbols that I have around, as long as they're not vague or things like that. But these are not, they're syntax. Right. Okay. In addition, note that ST is, according to the arithmetical pluralist, the theory of syntax they use to formulate their view. So this is a true theory of syntax, which is not a matter of convention or a matter of choice like the arithmetic theory is, right? This theory is the one that has to work for all the arithmetical theories, right? If they say any arithmetical theory is true, if it's consistent, that notion of consistency has to be cannot be a matter of choice like the others, has to be fixed. This is the whole point of Putnam and Kellner. You cannot have syntax being a matter of fact and the others a matter of choice. So the syntax needs to be a matter of fact, and this is what for instance Warren is trying to defend. So ST is true, period, right? And T is true in its own language. Good. We also know that these two definitions actually follow the primitive recursion schema, and so they're good definitions for this symbol. There's no reason to reject them, they're just definitions. And we also know that in ST and in T, all quantifiers are relativized to corresponding predicates. So remember, when we presented PA, everything was relativized to the predicate nat, and here we present the syntax theory, and everything is relativized to this predicate syn. All of this together entails that this theory, the arithmetical pluralist has to believe that this theory is committed to believing that this theory is true in its own language. Why? Because it's a combination of a theory is true in its own language with a theory that is true, period, namely ST, plus a definition. And everything seems in order because all quantifiers have been appropriately relativized. Happy to discuss this at Q&A, but this is an important part of the argument. Note, moreover, and this is the crucial bit, that and this theory is true in its own language, okay? In this language, the meanings of the expressions of the syntax fragment of the language and the meanings of the expressions of the arithmetic part of the language are the same as in the separate theories because we relativize the quantifiers appropriately. Which means that when the theory proves a sentence of the syntax language, the arithmetical pluralist has to take it as face value. It's the same meaning as in their own theory, which is, according to them, true, period, not true in a language, like just true. So everything that NST proofs that is formulated exclusively using the signature of the syntax language has to be taken as true. This allows us to show thesis 1, which is the arithmetical pluralist cannot possibly regard this as a consistent arithmetical theory. Assume they do. If they do, because this theory proves its axiom, that one, and the translation of this axiom, according to our syntactic translation, is PA is inconsistent. By observation 3, which says everything that T proves, NST proves its translation into the syntax language, we know that NS, and now this is our T, proves that PA is not consistent. And this sentence that I have highlighted there is a sentence expressed exclusively in the language of syntax, which means that the arithmetical pluralist has to take it as face value with the meaning it has in the syntax theory. So the arithmetical pluralist is committed to the inconsistency of PA. And moreover, by observation 5, since it's committed to the negation of this, it's also committed to the arithmetical pluralist is also committed to the negation of that, namely committed to the inconsistency of the big theory. And so they cannot take this to be a consistent arithmetical theory after all. That's thesis 1. So Warren said it was perfectly possible to take this as a consistent arithmetical theory. No, it's not. Thesis 2, assume these theories are recursively axiomatized theories in this language. They extend PA, all the things hold, but they're such that the first one proves phi and the second one proves not phi for some sentence phi. If the arithmetical pluralist regards them both as consistent arithmetical theories, by observation 3 again, we know that NST1, so adding the syntax theory to T1, will allow me to prove a syntactic claim, which is a translation of phi, and adding the syntax theory to T2 will allow me to prove the negation of that syntax claim. But as we said, the arithmetical pluralist is committed to every syntactic claim that follows from these theories. Therefore, they are committed to phi S and their negation and its negation, which means they are committed to a contradiction.
Can I ask one question, Lavinia, about this? Because, so just to check what the commitments are of the arithmetical pluralist here. So for the basic argument, for you, it wouldn't make a difference, but I wanted to see which versions of arithmetical pluralism are targeted. Are they committed to all syntactic facts being fixed, or just the consistency ones? Because one, for instance, could think that, I think that consistency facts are fixed, but say syntactic Ori sentences are, are open, being pluralist about syntax to that extent, not completely, but so the two claims, so one claim seems to be stronger than the other potentially.
So I'm not sure. They could say something like that. If they said something like that, then of course this argument wouldn't apply to any phi and not phi.
Yeah, exactly.
But this one would go. Does this argument go through? Yeah. But I'm not sure how easy it is to separate consistency claims from other syntax claims, right? Because they're all formulated in the same language and they entail. So for instance, if you have con PA, then you know that there is no sequence of finite sequence of finite strings of symbols satisfying certain conditions, but then you need to know something about how finite sequences behave. So basically, when Putnam and Kerner and I say syntax theory, what we mean is whatever theory you need to define consistency.
Yeah, no, exactly. But I was thinking something really, esoteric, like, esoteric, like Ori sentences for syntax in effect, right? So that's the kind of claim. So they would, and then, So the thought would be whether that's still compatible with some form of, not the kind of radical pluralism, because then you can translate it back to arithmetical pluralism, so you can maybe undermine the radical form of radical pluralism, but not of arithmetical pluralism, but not the a more moderate version where you say
yes.
consistency, is, the compia is really fixed. So you cannot have that kind of pluralism, but you can have two divergent arithmetical theories with regards to Ori sentences. In fact, that was
maybe. I think that sounds possible. I'm just a bit worried that then if you're defining consistency in a different way, you would have. Maybe I'm able to run a similar argument in which I replace ST with the theory you're using to define consistency now. But maybe you're right. Maybe that theory doesn't translate 1-1. Maybe only the consistency claims. So maybe only thesis 1 goes through, and maybe thesis 2. Maybe the pluralist can still say that they can endorse, or they can believe that seemingly incompatible arithmetical theories are true. Yeah, that would be something to explore. I think as long as they do it using a syntax theory like this, then they can't do this. But yeah, they might have some other things in mind. So that's it basically. Note that here we have these two claims, 3 and 4, which says prove something arithmetical, get the syntactic version, prove something syntactic, get the numerical version. And so the conclusion that we have is look, they're not really independent of one another, at least if consistency is defined this way. And it's not really then coherent to suppose that consistency and other syntactic notions are a matter of fact, while arithmetical truth is a matter of choice. But the argument is way more complicated. It has to do with putting the theories together and having this function that maps, right? And this is why the function was important, right? And this argument is actually inspired in an argument by Parsons, which we cite here. And so the argument itself is not particularly novel. However, applied to this case, I think it delivers this new conclusion that arithmetical pluralism is in trouble. I leave this possible objections to Q&A if you'd like to ask about them, and otherwise, thank you very much.
Thank you.
Yeah, thanks.